Please welcome on stage Samuel Giddins.
Okay, so I promise we're not going to talk too much about philosophy today. If you want to do that, we can do that, later tonight. So, about me, I'm at SE Giddins everywhere on the internet. You might have seen my name a couple of times before, next to some open source projects like CocoaPods and Bundler. I recently joined the brand new mobile developer experience team at Square, where it's my job to try and keep all of our iOS developers happy and productive. So that out of the way, there's going to be some programming language nerd talk ahead. For the past few years, especially since Swift came out, it's become really popular to talk about how programming languages work. But today I wanted to take a step back and talk about some of the things that we interact with but don't always notice, particularly with Swift. So back to the beginning of time. Objective-C. Fancy Objective-C like this. Except this really isn't the beginning of Objective-C. This is modern Objective-C with fancy new features. This is what real Objective-C was, the original. And it was funny, I noticed yesterday that I got this wrong because there was no ARC back in the day either. So I'm probably leaking memory here. So Objective-C, great language, we all love it a lot, right? So Objective-C was originally based on Smalltalk, so it's all about message passing. You don't invoke methods on objects, you send them messages, and the receiver of those messages, so self in your instance methods, gets to determine what to do with each message. So yeah, we still have that today in Objective-C. We have the ID type, which just means it's an object. You can send any message to it. It may or may not respond to that message. You may get an exception. But even better, from an ID, you can recover class and type information. You can do things like check, does this object respond to this selector? Does this object conform to this protocol? So you can ask an ID what it is, and it will be able to tell you. So IDs know what they are, and there you have an existential. So this sounds really simple, but it's quite a powerful construct. If you go back to something like C, an integer, for example, is just a bunch of bytes. You can lie to the compiler and cast that integer to a float, and you're never going to be able to recover the fact that it was an integer to begin with. So the power of existentials is provides features like dynamic casting. So this is where you can say, hey, maybe you've got some JSON, and you want to say, well, if the info field, if it is a string, let me unwrap that and use now my type-safe string. You can print any object, and you have protocol types. So all these features sounded really great. And when Swift was first announced, I was excited. But I also worried. These features sounded like they would be expensive. Expensive in terms of performance. What would happen if every integer or Boolean or floating point number would have to carry around type information? Wouldn't that make the language really slow? Really slow, like a language like Ruby. So I have kid, but in Ruby, like Objective-C, every object has an is a pointer. So in Objective-C, objects look a bit like this under the hood. They've gotten a bit fancier over the years. Now that is a pointer necessarily, it doesn't have to point to a class. We have tag pointers now. Some of those flags are also rolled into that is a pointer. But imagine if every integer was like that. That would be a lot of overhead. So, okay, take this 5 lines of Swift. How does it work? How can we go from an integer to an any back to an integer and have it print out that this works? So, as I was saying earlier, it doesn't work in a language like Objective-C or C, since an int is just 32 bits. Those bits could mean anything, and it's up to you as the programmer to know when you're writing your code that they mean an integer, or maybe that they mean a string. So I have some good news. Swift is smarter than C. This should come as a surprise to nobody. So let's unwrap how these 5 lines of code actually work. So line 1. This is real simple. It's just like C. We store a raw integer into some place in memory, and we call it I. Then this is just like doing stuff in Objective-C. We can check, like, is this a kind of this object? And at runtime, we go and we check the type metadata. We see what type it actually is. And so now we see the type is what we expect, and we're back to having a normal integer. And we can use it just like any other integer with 0 overhead. And that's it. Oh, wait, I forgot a line. So it turns out this is really the key to how existentials work. It looks real simple, but the compiler's doing a lot under the hood in this one line to allow us to go from an integer to an any type. So the compiler sees a cast from integer to any. It knows that an integer is a non-existential type, and any is existential. So the compiler says, okay, I need to promote from 5 to an any, and we store it as a separate instance. So we allocate basically a box. Compiler people love to call things boxes because they just hold things. So this box will point to type metadata. So this is what will say that our any is an integer. And the compiler puts that type metadata in at compile time. So it'll also point to things like thunks for protocol witnesses, so you can call methods on it. And we will point to or copy the underlying value, depending on what that underlying value happens to be. Now, in the case of 5, we'll just copy it because it's small. And every piece of code that refers to an any knows that it needs to indirect through the box to access any of the functionality, either to unwrap it or to find the type metadata or to call methods on it. And any code that needs type metadata for a non-existential type goes through the promotion process. So unfortunately, this promotion process is not like what you go through at work. It's not once you get promoted, you never go back. What the promotion process is all about is going from a concrete type, so integer, string, array, and wrapping it up into basically a tuple of here's the type and here's the value inside the box. So I learned all this stuff by working on a language called Trill, which is basically a wannabe Swift. And it's written in Swift, and this was a project started by my friend Harlan Haskins. He works on the Swift team. He has given some great talks about building compilers, including building Trill. But one of the cool things about working on this language was I got to see how a lot of Swift's concepts were actually implemented under the hood. And that helped me understand how a lot of these advanced language features actually work, and it helped demystify some of the magic. So in Trill, you have a type that looks like this. You have a foo type, and you have an integer and a bool inside of it. It looks just like Swift, really. You can call functions and do casting, do is checks, and most importantly for us today, Trill has an any type, just like Swift. And this is probably hard to read, but you can do a bunch of things that you don't really need to do in everyday code. Just wanted to give some examples here. So you can go from an integer to an any, you can do is checks, you can then cast. It may be hard to understand why this is so exciting for me. This takes a lot of work to implement the machinery for all of this. So this is some of that machinery. Trill has a small C++ runtime. It uses some fancy templating to make using this opaque any type in the runtime itself more pleasant. Pleasant C++. I know that's a bit of an oxymoron. I apologize. And it has this any box, which is what we were talking about earlier. And basically, the only thing you can do with this box is you can create one with type metadata, and you can take out fields from the value inside of it. You can put a value in it. And more importantly, you as the programmer never need to interact with this box. It's all in the runtime. The compiler, when it goes to do code generation, will create these as necessary. And in fact, this is the only place it gets created during code generation. So this means that the semantics of the language don't actually need to care about how any types are implemented under the hood. No, sorry about that. It means that only when we go to actually generate machine code do we need to care about wrapping up this type. And it turns out it's pretty simple. You have a value, you have the underlying type, and basically you check, okay, is the underlying type already an eddy? If so, great, just return it or copy it if necessary. If not, well, we generate an allocation. We find the typed metadata. We do some casting because LLVM requires quite a lot of casting. And then we just put the pointer to the value inside of the any box and return it. That's it. Okay, so that's great. what comes after dealing with types like any? And more specifically, what comes after that for Swift? Well, one thing that there is a great new Swift evolution proposal for that was posted on the forums maybe a week or two ago was about opaque return types. So this is really cool. It allows you to declare functions that return some protocol type. And you don't have to specify which concrete implementation it is. So you can say you're returning some collection, and that collection has some element type, in this case, a date. There's type erasure. Gwen Weston has given a great talk about how type erasure works in Swift. If you've ever used a type such as any collection or any sequence, those are type erased wrappers that allow you to hide the concrete type of the collection or sequence that they represent. And sort of the holy grail for programming language nerds is this fancy thing called generalized existentials. So if you've ever read the Swift Generics Manifesto, which I highly recommend reading, all the way at the bottom, this is on the list of things they'd like to do. And generalized existentials are basically a power-up for the any type that allow the any type to say, hey, we have an any that conforms to some protocol. So in this case, you could just say, we have some object who is a sequence, and that sequence's iterator's element type is string. Unfortunately, it seems we're still a few years away from getting generalized existentials in Swift, if we do ever get them. But if you want to find out more about them, you have a couple of options, such as reading the Generics Manifesto or downloading Haskell and playing around with Haskell. I highly recommend you try out Haskell. And there is a lot more to find out in this realm. Not just about how type systems work, which I know has become very popular, but also how the programming languages and the compilers we deal with make these features possible for us. And more importantly, how they make them possible by doing things in a very smart way, and making it possible to have powerful abstractions without paying costs even when you don't use those abstractions. And that's one of the great things about Swift, is it does have all these features. It does have runtime type information. It does have casting. It does have protocol types. And you can use those features when you need to, and when you don't need to, you don't have to pay any cost for them. Thank you.